Recording is on.
Okay, I would like to start with an image that captures Cardiff in its past and present. So on the left, you can see Cardiff in the full throes of the second phase of the Industrial Revolution, and you'll see rows and rows of trains carrying coal for export around the world. On the right-hand image, you can see completion of its transition into a tertiary sector economy focused on R&D and knowledge-based commercial activities. And as part of this transition away from the primary activities of fossil fuels and carbon-based mining, one of the region's key areas of investment and development is now in compound semiconductors, so atomically engineered materials made up of elements from the periodic table. So compound semiconductors are next generation materials, and they offer a performance increase over silicon in many applications. So you might have recently been aware of the shortage of semiconductors in the supply chain. These are mainly silicon devices, so it's a single element silicon, and the focus there being on microprocessors. So with compound semiconductors, we are talking about a different class of semiconductors. So this performance increase over silicon continues to drive the adoption of compound semiconductors, or CS, across many existing and new applications. So this includes the rollout of 5G, electric vehicles, and interconnected devices. And to give some examples, in power, CS is able to be configured for high voltage from 600 volts to thousands of volts, and is suitable for use in high temperature environments, in engines, for example. For 5G, CS can achieve radio frequency performance, so hundreds of gigahertz and 40 gigabits per second. For photonics, it's used for sensing, so high sensing capability, and data storage, things like interconnects. Also for LiDAR, that's light detection and ranging for autonomous driving. And right now, the CS cluster is the world's largest compound semiconductor cluster. It offers world-class research from institutions such as the ICS, which is the Institute for Compound Semiconductors, and CSC, which is the Center for Compound Semiconductors, which offers prototyping and routes to commercialization for volume manufacturing. So the vision for the cluster, or CSConnected, is enabling contemporary industrial commercial applications with a new generation of compound semiconductor materials. So the cluster aims to provide support to avoid what's commonly known as the valley of death in product development when implementing new CS technologies. So this is the technical readiness scale, which reflects technical maturity of a product. The red blocks entry TRL levels, so offering basic research and proof of concept. The orange blocks that you see at the center, validation of the equipment in the lab, the product, and early prototyping. The green blocks show real-world prototype development and actual flight-proven successful mission product launch. So in terms of this being the TRL levels being a NASA-developed system, if we had JFK's speech again, then that would be TRL 1. And Neil Armstrong splashdown and successful recovery following the moon landing would be TRL 9. So here we have an overview of the founder members of CSConnected and the CS community. This, in some way, follows the layout of this follows the TRL slide we just looked at. In column 1, we have the ICS, the Institute for Compound Semiconductors, and CISM, which is the Center for Integrative Semiconductor Manufacturing, both of which offer fundamental research, including research scale wafer manufacture and design for manufacturing services. In column 2, we have CSC, which is a joint venture between IQE and Cardiff. CSE offers advanced materials development and developments for new and emerging applications, both for business and academic prototyping, which is quite unique. And this is an essential pillar to avoid the valley of death we just looked at. The CSA Catapult offers systems integration expertise, and that's integration with electronics, designing devices for manufacture, and enhancing robustness of new products. And then column 3, contract manufacturing, we have IQE, which is a publicly listed company on London Stock Exchange. It was formed in 1988 to provide MOCVD manufacture of wafers. Then the company was very much focused on LEDs, lasers, and photodetectors, but has since, through mergers and acquisitions, it's very much a global venture, focusing on things like RF and mobile comms and optical devices for telecom applications. And the current focus for IQE is the development of its mega foundry based in the region, with 100 high volume production tools present. We also have Nexperia Newport Wafer Fab, where the focus is on power applications, so MOSFETs and IGBTs, analog and CS automotive grade products. The facility itself was formed in 1982 and has capability of 35,000 8-inch wafer starts per month. So it's very, very high volume with a focus on those MOSFETs and IGBTs for things like power conversion, switches, operating pumps and fans, and electric power steering in vehicles, and AC to DC conversion. Microchip is an advanced packaging solutions company. So it has design tools to reduce the risks involved in packaging devices and reduce the time to market of those devices. SPTS is a KLA company that designs and manufactures systems for use in compound semiconductor, so etch and deposition solutions, plasma, chemical, and molecular vapor deposition. And then we have our supply chain partners in column 4. So these are companies that have joined the cluster since its inception. Rockley Photonics is developing healthcare wearables and machine vision applications. The company was founded by Andrew Rickman, who was founder of Bookham. Went on to be a successful company listed on NASDAQ. Rockley's listed on the New York Stock Exchange and is currently developing silicon-based products in those applications. Microlink develops and manufactures photovoltaics. These are very high efficiency photovoltaic panels that are flexible and also lightweight. So the applications there are many, but one of the key applications is for unmanned aerial vehicles. And in the final column, you can see the applications that are targeted from the technology. So here we can see the effect of Moore's law. So here we are talking about silicon microprocessors and the amount of transistors per chip. So where this started in the 1970s with a few thousand transistors per chip, we're now at a point of approaching 25 billion transistors on a single chip. And this requires processing really down at the atomic scale. So there are issues with this, running into technical limits, including quantum effects and so on. So we can't continue with this technology indefinitely. So there has to be a different approach. This slide shows the current dominance of Korea and Taiwan in semiconductors. So these are memory and microprocessor devices in the main. The US, China, and Japan are competitive, but the rest of the world, including Europe, really need to catch up. Compound semiconductors, CS, is about 10% of the semiconductor market, and the semiconductor market as a whole is just over $500 billion per year. So somewhere in the region of 50 billion per year for CS. And recently, the European Union announced 145 billion fund really to make this happen. So evolution has often been defined by the tools of the time. We've recently had steel and plastics and so on, but we feel the next material will be semiconductors, so the semiconductor age. So we now have the ability to atomically engineer materials, and compound semiconductors are engineered using elements from the key groups in the periodic table. These can be groups 3 and 5, for example, and 2 and 6, creating materials like gallium arsenide and indium phosphide. But the different materials are developed in a way that they use to create chips and components to match the needs of the application. CS is very much at the center of new and emerging applications. We are increasingly hearing more about these applications, which makes the field ever more exciting. The technology has been around for a few decades now, but the emergence of these applications is really driving a lot more interest. And the superior performance of compound semi continues to drive their adoption. Which means that it's a key emerging technology that underpins many of these contemporary industrial and commercial applications. Here we look at sensing applications. In the main, the use of VCSELs. So VCSELs are vertical cavity surface emitting lasers, and they dominate the applications in this field. The use of various techniques are involved, but eye safety is quite often an important consideration in these. VCSELs are expected to reach $2.7 billion market size by 2025. Automotive LiDAR is predicted to emerge medium to long term. And if you have an Apple iPad Pro, this uses a VCSEL from a company called Lumentum, which have 68% of the market. In 2020, there were 325 million VCSELs used in iPhones around the world. And there are competing companies, AMS and Trumpf in Germany, having shares of 15% and 7% of the market, respectively. Now we look specifically at handsets and wearables. Again, VCSELs are used in the main for sensing. We have gallium nitride for base stations, handsets, and phone chargers. Overheating is one of the main drawbacks in these areas. And gallium nitride safety complies with standards on this front. It provides better processing power with less heat. Rockley Photonics that I mentioned earlier, a cluster partner, they develop in a spectrophotometer on a chip as a sensing module. And this is then developed into a clinic on a risk, as they've described it, providing digital health information such as body temperature, blood pressure, hydration, alcohol content, all integrated into a single wristband, single wearable. For connectivity, there are numerous applications. This could be connecting people with one another, connecting IoT devices to the cloud, connecting cars in unexpected ways that we just don't yet know about. IoT, the component market continues to grow and is worth predicted to be worth 80 billion by 2025. And by that time, there will be 30 billion IoT connections globally. Electric mobility is highly dependent on compound semiconductors. So EVs, or electric vehicles, require VCSELs for sensing, things like face recognition, gesture control, alertness monitoring. We have gallium nitride for power transmission, LiDAR for cross-traffic alert and blind spot detection systems, and 5G for communications between vehicles. For security, compound semiconductors plays an important role. Have gallium antimonide, indium antimonide required for night vision, thermal imaging systems, and gallium nitride for high performance radar communications. Have VCSELs for data security and other fiber communications, and also quantum technologies, things like quantum key distribution, which is a very new and emerging application that's required for secure communications. So here we're looking at an example, what happened to BT. BT first to develop ultra-fast broadband technology. So it's developed in the UK and exported around the world, eventually developed and improved somewhat by Huawei and ZTE. Eventually, this new version has made its way back to the UK. And we include this as an example of what we would very much like not to repeat for compound semiconductors in the areas that we are working in. So globalization of compound semiconductors and silicon-based semiconductors. In the main here, we are looking at silicon. So this started in the main in California, but developed further in Korea and Taiwan, which is now dominant. Supply chains for this industry tend to be close and perhaps need to be close, much like Detroit Motors, for example. We have 4 clusters around Europe. In Grenoble, we have a cluster based around ST Microelectronics, Eindhoven, based around Phillips and NXP, now NXP, Leuven, based around IMEC, and Dresden, where there's presence there with Siemens and Infineon. These are well-established bases, but in the main based on silicon. So CSConnected is the newest European cluster, and first to focus on next generation semiconductor materials. We are zooming in on CSConnected in the region. So this is roughly a 60-mile radius where we have all members present, with CSConnected providing the glue, essentially the framework, to make this a coherent effort from all members, and to drive the effort in terms of permanence and expansion of the cluster. The investment to date totals roughly $1 billion so far, covering all the TRL levels, so 1 to 9. And this has allowed us to update tools and systems that are in place. The key companies have greater than 30 years of presence within the cluster, but prior to forming CSConnected, they were found to be approaching or serving the same customers around the world. And the idea being to come together in order to leverage that experience in a way that's working together. IQE and Cardiff formed CSE, and that was the joint venture mentioned earlier. This organization provides outsourced innovation facilities. So specifically looking for opportunities of greater 3 years or more, 3 years from market. So TRL 6, 4 to 6. The Catapult will work on applications that come out of CSE. So taking a product or building the product around wafer or chip components. And then we have the ICS, which is a £75 million facility, and CISM, which is another £90 million investment. We also have the IQE Mega Foundry, which is looking to place 100 systems, 100 tools, all for volume manufacture. Recently, the group of members have secured a Strength in Places grant, which is an all-partner project, building on the expertise, and is a collaborative research and development effort. And this is currently underway. So as we move into the next phase, CSConnected will evolve into a membership organization, and we expect this to join up with other UK and EU supply chains. We would say for core activities, we are looking to retain IP and jobs within the region, but for downstream activities, we can't possibly ask the same or expect the same from supply chains downstream. So we're looking to to build those relationships within the EU and the UK. Finally, we have some examples of the R&D packages within currently going through the CS cluster via the Strength in Places Fund. So in column 1, we have next generation optical comms and sensing. So this is for building high capacity data centers, and also for LiDAR for autonomous electric vehicles. In column 2, we have large scale gallium arsenide wafers. So some multiple applications, but including the flexible PV or photovoltaics mentioned earlier. Column 3, we have novel CS fabrication tools, so scaling wafers and device fabrication for volume manufacture. And in column 4 there, we have advanced process development for 5G and electric assisted vehicles. So this is for 5G components and also for miniaturized electric vehicle motors. So that concludes my presentation. Thank you for listening. And please contact me if you are interested in any of the aspects we've looked at. I'm happy to take any questions, answer any questions that you may have. Thank you.
Thank you, Phil. For now, there are no questions in the chat. Maybe our participants I can motivate them now to ask some questions. For those who might have not found the chat yet, it's if you scroll over your screen, you will see a bar of symbols popping up, and there is the symbol of a speech bubble, which also has the sign chat öffnen, open chat, and there you can find the chat and ask questions. Phil, would it be okay to post your contact to the chat for the participants?
Yes.
Your email? Mm-hmm.
So I've placed my email address in the chat. If anybody has any questions, any interest in the cluster that you'd like to contact me about, more than happy to for you to send any questions by email. If you look at the CSConnected, so it's csconnected.com website, there's also contact information on there, including a telephone number if you prefer to call directly.
I think there's still no questions, so we could wait a few more moments.
Okay. Thank you.
Okay, then I would say that we finish for this forum. The email of Phil is in the chat. Thank you for participating. Thank you, Phil, for presenting, for the interesting presentation. I would then say goodbye to all, and I hope you enjoyed the remaining fora of the day. And you can return to the main stage or the main room of this conference. If you go on the left of your screen, there is, depending on if your computer is set in German or English, Empfangshalle, or I don't know how the English word would be. My computer is set in German, so this way you can return to the main stage. Thank you, everyone, for attending today.
Absolutely. And just to second that, yes, thank you, everybody, for your time. Appreciate it. It was of interest. Thank you.
Thank you. Goodbye.
Bye.